I'm Andrei. I'm super excited to be a part of SciPy, at least virtually. And before I even begin, I should really thank the organizers for letting me do this talk virtually. I know these exceptions require a non-trivial effort from a lot of people, so I just wanted to say that I truly appreciate all the work everyone has done to let me speak. So let us get going. So today I will be presenting Emukit, and that will be a relatively lightweight talk, as I think my main goal here is just to make sure that you all listeners have a very good intuitive understanding of the package, and I hope to motivate you to check it out further, so don't expect crazy math or the complex engineering tricks as this talk. What is Emukit? Emukit is a Python package for decision-making under uncertainty. And I thought the first thing we should do is just to really understand what does this phrase mean, decision-making under uncertainty, right? So let's start with that. So our life is, as you may have noticed by now, is surrounded by complex processes, right? And these complex processes, I mean, sure, they could be training a complex neural net on your computer, or maybe doing a experiment in the chemical lab. But it also could be just baking cookies or doing your workout or whatever. There are a lot of processes around us, and the more I think about them, the more I realize that they're all complex, non-trivial, and they depend on a lot of factors, right? But obviously, as scientists, we like to throw functions on everything, so we can say that these processes are separate functions. Each one of them is f of x gives y, where x is some sort of maybe hyperparameters of the model, or maybe maybe the amount of ingredients you put in the cookie recipe, and then the output y is some sort of a way to measure the process, right? The accuracy of the model, or maybe how many cookies we sold in a given day. These functions are black box, meaning that we don't know exactly how that works, right? We might have more or less of a intuitive understanding, right? But we don't know the exact process to all the details, right? And a lot of times it could be that we want to do something with these functions, right? So could be we wanted to find an optimum, like minimizing or maximizing, as we just heard in the previous talk, right? Or it could be that we want to calculate an integral of it, or maybe just learn how this function behaves on a certain input part of the input domain. But the thing is, this function and this process are really complex and expensive. And expensive could mean they take a long time to run, or they take a lot of money, or they could just increase wear and tear of our hardware. Whatever that is, they are just expensive, so we cannot afford to run them 10,000 or hundreds of thousands of times. And you need to be smart, right? So what to do? And I'm not going to push any buttons and say that this is the only way to be smart. But one of the things that you could do is, when you are in this situation and data is scarce, is to be Bayesian about it. So what do we mean by that? First of all, we start with some basic like intuition, some kind of an idea of what the process might look like, right? Just our internal belief, right? Then we, based on that belief, we decide that we want to see how this process actually behaves. We want to try it in just one point. We evaluate it at that point, observe the output, and with that, with whatever came back, we update our belief, kind of, okay, we need to readjust a little bit now that we saw how it behaves in this particular input. And we go through this iterative process a number of times until we are happy enough and satisfied with our knowledge that we gained, right? And hopefully by being like strategic about where do you run next, you just run way fewer iterations and don't incur all the cost of completing your task. There are many flavors for the process that I just described, and they have specific names depending on what you want to do, right? If you want to optimize a function, this is something that is known as Bayesian optimization. if you want to integrate it, this is something that's on Bayesian quadrature. And finally, if you just want to learn it on a certain, how does it behave in a certain part of the input domain, then this is known as experimental design or also active learning. But despite the fact that all these methods have like different names, they have different goals, they have different communities working on them, they all conform to the same high-level algorithms that we just mentioned on the 2 slides ago. And that is the key realization that we have built the Emukit around. So now we are ready to revisit this phrase of decision-making and uncertainty. Why do we say decision-making? Well, each point that we evaluate is an expensive decision that we're making. And it's obviously non-trivial, and this is an important, and so that is why we have the decision-making bit here. And why uncertainty? Well, first of all, we have we never really see in the world the exact observations. Whatever process you run, you will probably get back a noisy outcome. So you need to account for that, and you don't even know all the sources of the noise. And the second reason is, even if we have data in one point, it only gives me some rough idea of what the function in the process behaves like around that point, right? So that is also something to think about, and some sort of uncertainty in the process. Now that we have some understanding of the goal and the vision of Emukit, let's talk a little bit more about its scope, right? So the process that I've just described can be seen as going from the models to the methods to the tasks. So I'll decipher this now. Model is the belief that we mentioned, right? It's our data-driven representation of the objective function, and as well as our uncertainty about this objective function, right? Oftentimes, you will hear the community refer to it as statistical emulator as well, right? Because it's important for it to be probabilistic so we can actually quantify our uncertainty. The most popular model for this purpose is Gaussian process, but it doesn't have to be. Sometimes you could see random forests, Bayesian neural nets, ensembles of neural nets. There are many different options. So as far as scope goes, Emukit is not a modeling framework, so we don't actually provide any of these. We expect the users to come with the models defined in the framework of the choice. There are so many different good frameworks around for probabilistic modeling that we didn't feel the need to write our own. With one exception that you can see in bold here, multi-fidelity. And the reason for this is that we had a lot of interest in multi-fidelity modeling and Gaussian process, but we just couldn't find any good software for it. So we thought, why not, and made it a part of the package. But generally speaking, Emukit is not a modeling framework. So yeah, users are expected to choose a framework they'd like and just plug the model into Emukit. Now comes the method, which is the heart of Emukit, the main objective of the library, to provide the iterations of this method and in one unified way. And so we spoke about them before, and we'll be talking about them again, so I won't dwell a lot on that slide. But after method comes the task. And like you see, tasks are meaningful things that you would like to actually do. Like, unless you are a student working on an assignment, you don't actually want to compute an integral or find an optimum of a function, right? What you actually want to do is maybe get better results from your experiment, or maybe launch the rocket into space, or maybe reduce the cost of whatever process you're running, right? But so these are actual business or scientific reasons why you're using one of the methods we mentioned before. And there's really no limit to what the task could, what forms the task could take. So we didn't really even try to provide any sort of a functionality on that side as well. Instead, we just build a lot of tutorials and examples so that people can understand what kind of things are possible in theory with Emukit. So now that we probably have a little bit of a intuition about what Emukit is, let's talk about how to use it. Right? In the very vanilla, simple way, what you do is you kind of define the optimization problem, integration problem, or active learning problem in a similar way. So like I said, on this side here, we can see that the model here is defined by GPy, which is external to Emukit. And then we wrap it into something that Emukit can digest and talk to the model. We provide a couple of wrappers, and they also conserve examples for people using different frameworks for which we don't have wrappers, and we plan to expand it as well. Then you define your input space, and in this particular example, we'll also define something that is known as an acquisition function, which I'll explain in the next slide. And then we're ready to go, and we run the decision-making loop. But if you are using Emukit in that way, you're barely scratching the surface of the package. Let me explain why. So the key of the key features that the key thing that we wanted to achieve when we built Emukit was the extreme flexibility of building this method the way you find the most interesting for you and useful for you. And all of them, at a certain level, consist of the same set of components that you can swap in and out, right? So what is this component? Regardless of whether you're doing quadrature or optimization, these are staying the same. First of all, there is an objective function, which is the process we're trying to study. Then there is a model, which we already talked about. So this is our internal belief. It stores all the data we have learned so far about the objective. Then there is an acquisition function. This is the interesting bit. It's a mechanism for us to use the model and the data it provides to make a decision where to execute the next next observation. And another thing that acquisition does for us is it balances something known as exploration versus exploitation trade-off. Exploration is our desire to learn the entire input space, all of it, and exploitation is our desire to stick in a particular small subset of the input points that just looks promising, right? So you kind of want to do more because sometimes you don't really know what the best point is, and sometimes you don't want to be stuck into the small one, but sometimes you really want to double down in the small region, which looks good. So you need to somehow balance it, and acquisition provides this mechanism. Finally, there is something known as stopping criterion, which is a way for us to say that like we've done enough, right? Maybe we're on a budget of time or iterations or whatever that might be. This is an abstraction to let us know that the decision-making loop should go no more, right? And the key idea that we had in the back of our head when we built the Emukit is that all of these components should be easily replaceable, swappable. People should be able to compare them to kind of facilitate research on these methods, right? So how did we achieve this sort of flexibility? Well, to be honest, there's no magic or no tricks. We just followed some well-known engineering practices. So for example, here we have obviously trimmed down. There's a lot more code in the actual source, which you can look up, but this is the crust of the decision-making loop that we have. And the point here is that it operates on the high-level abstractions. It doesn't know whether it's optimizing or integrating. It also doesn't know how each component will be implemented, right? But it just knows the interface that the components have to adhere to, and it just knows that these components can produce some common data exchange format, right? Which in our case we chosen to be a NumPy array. That is pretty much it. That's it, and that's like all of the methods I've mentioned to you. No matter if it's integration or optimization, they all conform to this sort of structure, right? So we just try to make it very abstract so that the actual implementations don't really affect the general flow of the decision making. Another example would be like here when two components need to communicate. For example, here acquisition needs to use a model and require certain functionality from the model. Here, what we did, we defined this functionality as an interface, which the acquisition expects the model to adhere to, and then it doesn't really matter how the model does it then, as long as it implements these two functions. For this particular case, it apparently has to be able to do certain operations with the hyperparameters of the model, sample and fix them. And then acquisition function doesn't really know what kind of model it is, whether it's Gaussian process or whether it's a neural network. It doesn't matter as long as these two are implemented. It also doesn't matter whether we're using TensorFlow or PyTorch or NumPy or Piano, whatever that might be that we're using to actually do the linear algebra behind these models. Again, there is nothing in Emukit that restricts you from using any of this. And these two examples shows the main thing that I'm trying to kind of say here, is that there's no rocket science, there's no crazy engineering that we did for Emukit, really. It's kind of simple, just following the basic practices, maybe solid principles, occasionally some design patterns from again 4. And it's like apparently when applied right, it allows you to build a pretty intuitive and flexible library, I'm happy to report. But wait a second. Let's consider what did I just say. So I said that we have components interacting with NumPy arrays as a common data format, right? And I also said that Emukit is agnostic to a particular modeling framework. So if you think about this for a second, it becomes apparent that these two main features that I've been telling you about, this ability to be like flexible and to really not care how the linear algebra behind is done, they also result as the biggest drawback of Emukit, which is its performance. So let me explain a little bit better what I mean. There are tools in the entire ecosystem of scientific Python, if I may say, which I consider to be the most similar ones to Emukit, BioTorch and Trieste, and they serve as the great examples of this performance issue, because each of them depend on they made a very deliberate choice of running on top of PyTorch and TensorFlow respectively, right? And they enjoy all the richness of features that these monsters provide, including GPU acceleration. Now, Emukit making the choice of deploying on exchanging everything in NumPy array, and also not really knowing how the modeling is done behind the scenes, just cannot have this thing. It cannot be GPU accelerated. We simply have no idea how the underlying linear algebra is done. And the fact that we are constantly switching back and forth whatever model is using for its data representation to NumPy means we're constantly breaking the computation graph if it exists. So yeah, if you are considering diving into one of those methods and you require speed, just keep that in mind. You still could use Emukit, it would be just slower. But then, okay, you may ask, if performance is not something that Emukit excels at, what does it excel at? Why would they use something like Emukit, right? So first of all, it's a rapid prototyping. Like I said, that was our original goal, to support research in Bayesian quadrature, in Bayesian optimization, in active learning, to help people iterate quickly, fail fast, try things out, and not really write any boilerplate and provide all of it for them. So this is the intended purpose of the package, and we have had some good feedback from researchers doing it, and I think we achieved that goal. It wasn't, to be honest, intended, but it turned out that the package is pretty intuitive and expressive. It makes it really good for teaching. And so we know that Emukit was used in the past and is still being used in some places, in multiple universities actually, as well as summer schools, for teaching Gaussian processes, for teaching statistical emulation, Bayesian optimization, and certainty quantification kind of studies. So that is I guess, the feature number 2. And then, amazingly, given the size of the scientific Python community and the speed at which it develops, it grows, and packages come out, to the best of my knowledge, and please do correct me if I'm wrong, there are still some areas in which there's some features of Emukit that are unique to it. And they were unique to it when we originally developed it 5 years ago. So I find it surprising, but apparently Emukit is still the best package there is for Bayesian quadrature, which is admittedly a small community, so maybe they just don't need anything else, right? As well as multi-fidelity emulation with Gaussian processes. So what are this is where the library is right now. So I wanted to close with briefly talking to you about what our plans are and what the future holds. So first of all, I don't know what you thought about the code that I shared with you about the basic use of the library, but I didn't find it easy at all. Like, you need to bring your own model, and you need to know what the you need to know exactly what your domain is. These are all things that are not really friendly for an absolute beginner who just wants to optimize the model, right? I would love to be able to say that here is a piece of code that optimizes your model with Emukit in 3 lines of code, but I simply cannot say anything like that because this is not the way we develop the package. So I think there's a lot to be done there. There's also, admittedly, we are still not, especially from the point of view of uncertainty quantification community, we're still not feature complete for them. The main things would be sensitivity analysis, which I didn't even mention in the talk. We kind of have it. It's really in the very, like, kind of just starting sort of way, implemented in the package, and we want to expand it a lot, but it's one of those things that we never got around to do it. But that would be very important if we wanted to appeal to UQ community. And another thing that was pointed out to me by one of the users of Emukit is Bayesian calibration. So really some sense to work on here. And one more thing is the integrations with other tools in the ecosystem. That is, again, something that we probably should consider more seriously in the coming months and years is, things like SciPy, things like Raytune, Aptuna. All of these libraries allow for custom optimization backends. And frankly, there is no reason why we should not provide Emukit with one of those backends. BioTorch does it, as other libraries do it. So we probably should do it as well. And final thing I want to mention is this is one of the main reasons that motivated me to try and get this talk at SciPy in, is that maybe there are ideas in the community of what could happen to the package, and I'm really looking forward to the comments, the questions, maybe some discussions that can arise as a result of this talk from presenting to all of you Emukit. Because I'm really interested, and maybe there are some ideas out there that we haven't really considered. So please, I'm kind of trying to say that we're just looking for any kind of feedback. Before I close, just a shout out to the team. We had this bunch of awesome people. Some of them still make it effort to run the tool and answer questions and make sure that the Emukit is alive and updated and gets new user updates regularly. There's also some original team here. And with that, thank you very much for your attention. I'm looking forward to your questions, whether they'll be in the room or in Slack or elsewhere. Thanks so much.
All right. Questions for Andrei? Any questions? No one? Okay. Sorry.
No worries. Okay. The image quality here for us was a little tricky to fully get the insight of your code samples. So can in 2 sentences you help me wrap up my mind as to what problem, this is, oh, my English module is just so wonky. Can you explain again the examples you showed and how Emukit helps getting to solution?
Sure. So let me give you one example that I think is quite famous, because that's the example that Google used when they when they released their own service for hyperparameter optimization. Let's suppose you're baking cookies, right? So you have, this is clearly a complex process, right, which we can say is a complex function that takes in a couple of inputs, you know, the different ingredients, like the measures of the different ingredients, the time you baked it for, the time you spent to preheat the oven, and things like that, right? And the output is, let's say you are, I don't know, you're selling cookies. So the output, the better the cookie is, the more you sell in a day. I don't know, it's a probably over approximation, but it's over simplification, but it's probably, will probably serve. So you naturally want to find the best recipe so that you sell the most cookies, right? But you can't really try all of the different ways in this recipe could work, right? All those different ways you put ingredients together, all of different measures of them, all of the different times to to keep them in the oven, because it's just too much of a tries, right? And it will probably spend years, right? So you need to be smart about this, optimize this function gradually, step by step. Trying one time, trying twice configuration of the input, seeing what the output gives, what is the output of it, right? And deciding where to go next. And you kind of try this iteratively, one by one, very slowly, but trying to get as much information as possible from each point, right? So you are optimizing a complex black box function, right, in an iterative way. And this is a kind of problem that Emukit helps solve, right? Optimizing such function, integrating such function, or just learning, reducing your uncertainty about this function in certain, like over certain input. Does it make any sense? Does it help?
Yes, thank you so much. Follow-up question.
Sure.
Do you have some users you can talk about and what problems they take on using Emukit?
Oh yeah, of course. So yeah, like if you're interested, we discussed some of that in the papers that we submitted to proceedings, but I can probably start by saying that we have a, let's see. So we had a couple of examples. Like Emukit was originally developed by, like when I was an employee in Amazon, and we had a team in Amazon Research that was doing it. None of us actually works there, and Emukit is fully neutral right now. I just want to say that. But back in Amazon, we used it for a couple of projects. One would be you would optimize I think the advertisement on the website was using it to optimize the placement of adverts. And another one would be, I think there was some sort of a optimization going on in Amazon Video in the bitrate that the users receive, right? Based on the bandwidth and the overload in the network. Outside of that, people used Emukit a lot to optimize, like the engineers actually used it to optimize the run of the services. Let's suppose you have non-trivial setup in your cloud when you run a bunch of services together, and there is different bits and bobs that you can turn that you can also formulate as a optimization problem, right? People have used it for there's obviously a lot of hyperparameter optimization with the classical problem that people also can, formulate as an optimization problem to solve with Emukit. So it's really anywhere, as long as you can find a non-trivial black box functions that you can't really run for 10,000 times, but you still want to optimize in some way, where we can enjoy a lot of use. Does that make sense?
Yes, thank you.
Thank you so much for the question.
Any other question?
Hello. I was
Hello.
wondering about batch optimization, if there's any kind of work on that you're looking at, and anything in that area, because I know that's a very interesting age, like experimentalists. They might want to do several different experiments without having to go back to the computer or in parallel.
Yeah, for sure. Great question. So we have, at the moment, I think we only support it for Bayesian optimization. There is a very well-known technique for that, an empirical technique. What was it called? Local penalization. Here we go. So that allows you to build the batch sizes of reasonable size. And yes, this is something that you can do right now with Emukit. There is really no reason why you can't try that with other methods, particularly the active learning. But honestly, I have never tried it. Then there is a couple of I think ongoing thoughts about using other similar since to build once local optimization came out, there were a lot of additions to it, like building on top of it. We haven't got around to implement them yet, but this is something that we could actually also do. But yeah, to some limited extent for Bayesian optimization, you can do batches right now with Emukit. Thank you.
All right, we are out of time for more questions. But if you have more questions for Andrei, you can post them on Slack. Let's take Andrei one more time.
Yeah. Thank you again.